Okay, we're going to look at a problem, typical problem involving a box-shaped vessel and a vessel having an angle of Loll and having to calculate that angle of Loll, and then also the GM at the angle of Loll. So we're given a length, breadth, a draft of the vessel, it's kg, and we're going to put 620 tons of cargo on deck and this will create an angle of Loll. So, as always with stability, establish which formulas that you need to use. So we know that tan theta is minus 2 times gm over bm. Okay, what's gm? Gm is km minus kg. So we will have to work out our kg in the normal way. And then km, how are we going to get the km? Because it doesn't mention hydrostatics. So we know that km is kb plus bm, so we need kb. It's a box-shaped vessel, so whatever our new draft is after loading, we can simply halve that and get the kb. And we know the formula for bm, lb cubed over 12v, or b squared over 12d if it's a box-shaped vessel, so we can get the bm and the kb, which gives us the km, gives the gm. And of course, when you've done that, you've actually got the value of bm required to solve the problem. So what we need to establish here initially, of course, is our new kg. Well, we don't know the weight of the vessel, but because we know its length, breadth and draft, we can work out its displacement, length times breadth times draft times density. We've loaded 620 tons at kg 7.78. We've used 4.18, which is of course is our initial kg. So now our new kg is 4.612. Now to find the load draft, we know that weight is length times breadth times draft times density. Well, we know the final weight. The length and breadth haven't changed. The density of course hasn't changed. So we move the formula around and we can now calculate the new draft, because of course we need the new draft to get the kb. So our new draft is 4.773, kb is half that, 2.386, and as I mentioned earlier, bm is b squared over 12d, lb cubed over 12v, you'd get the same answer. So there's our bm 2.113, add the two together, that gives us our km. We've got our kg here, which we bring down, and as you can see here, the gm is a minus value. Had you got a plus value in this problem, you'd have done something wrong. You have to have a minus value of gm in order to have an angle of Loll. The gm must be initially negative to get the angle of Loll. So put the information into the formula, tan theta minus 2 times gm over bm transverse, and we get an angle of Loll of 18.1 degrees. So reasonably straightforward, as long as you know which formulas you have to use. Standard formula for the GM at the angle of Loll, it's minus 2 times the initial GM over cos theta. Cos theta is the angle that you've just calculated, therefore the GM at the angle of Loll, that becomes positive, is 0.238. So remember, initially your GM is negative, then once the vessel rolls over and settles at the angle of Loll, you then have a positive GM. So it's a box-shaped vessel, you can't use hydrostatic particulars, but finding the km and obviously the bm is reasonably straightforward. The one slight problem students may have had here is forgetting that of course your draft has changed. Once you've loaded the cargo, you had to calculate the new draft by moving the formula around. So you had to get your new draft, which gave you your new kb.